All right. So the last time that we spoke, we were talking about cosmology anyway, the FRW equation. And what this was A dot over A squared over 8 pi g over 3 times the energy density rho minus k c squared over A squared. So what the FRW equation did is it related the expansion rate of the universe. So remember that A is basically the scale factor, which tells you what the overall size of the universe is at a single moment in time. And A dot is how that changes. So A dot tells you how the universe scales in time. And it relates that, so the overall dynamic change of the universe's size, to what's inside it. And what's inside it is this energy density here, rho. So rho is the energy density joules per meter cubed of whatever energy there is. Could be mass energy, could be radiation, could be photons, could be dark energy, for example. And then subtract by the curvature. So the interplay between these two things, curvature and the energy density, will basically tell you what's happening to the left-hand side, what's happening to the size of the universe. And basically this says that no matter what, unless the right-hand side somehow cancel each other out at some point, you will end up with expansion or contraction at some point. So the left-hand side, A dot over A, such an important term that we call this the Hubble term. This is h of t. Today that's a constant, h naught. Rho is the energy density of anything. And in principle, we have three of them. So the energy density is really the energy of matter, the common stuff, the protons, electrons, and basically all the atoms and all the regular matter that you have in the universe, plus the radiation density. So these are photons and basically anything between X-ray, gamma rays, and radio waves, plus the dark energy term, which is rho lambda. And that's that weird dark energy stuff where if I took a box of empty space and emptied everything inside that box, so no atoms, no photons, I would find out there's still some energy inside here. And the energy inside there is the density of energy, of dark energy, times the overall volume of the box. And how much that is would be a very small number because rho lambda over here isn't very large, but it would be non-zero. So the FRW equation, when you put this all together, is h squared over 8 pi g over 3, and the sum of all of them, minus the curvature, k, c squared over a squared. And so k can really only be a handful of things. K is either plus or minus 1 or 0, and 0 is flat. So what I wanted to talk about was basically how we determined that we have an overall flat universe. And the way you do that is by first rewriting this equation, the FRW equation. And we write it in a slightly more convenient form. And the way we do that is we define a critical density. So we're going to call this rho crit. And the critical density will basically just be the density, this critical amount of density, such that if there's more than that critical amount of density in the universe, then my curvature will become plus 1. So k will become plus 1, and I'll have a spherically curved universe. And then if I'm at exactly, let's say, exactly the critical density, my universe will be flat. And if I have slightly less than that critical density, I will have a negatively curved universe. So rho critical will basically tell you what the curvature is of the universe and when it changes. It changes at this exact value of density. And rho crit is equal to 8 pi g over 3. Whoops, this is the opposite. This is 3h squared over 8 pi g, like that. This is my critical density, meaning that if I'm over this, my curvature will become plus 1. If I'm equal to this critical density, so I find out that rho m, rho lambda, and rho radiation equal to this critical amount, then my universe stays flat. And if I add up all of these energy density terms and I get less than that critical, then my k will be negative. How do we make that deduction? Well, take a look. So if this is my critical density, then what you'll see over here is that this is basically very close to 1 over my critical, 1 over rho crit. In fact, if I divide the left-hand side and the right-hand side by h squared, then this term here in green will exactly be 1 over rho crit. And that's what I'm going to do. I'm going to divide both sides by 1 over h squared, in which case my FRW becomes this plus rho m, rho rad, and rho lambda minus kc squared over a squared, h squared. So once I've divided the left-hand side, you'll see that this is exactly 1 over rho crit. Okay, so I can rewrite that as 1 equal to rho m over rho crit plus rho rad over rho crit, and then finally dark energy over rho crit minus k c squared a squared h squared, like this. So everything here, these are all dimensionless constants. Okay, so rho m over rho crit doesn't have any units, nor does this term or that term. They're all ratios, they're all fractions. And what you can think of these fractions as being is basically what overall fraction of the critical amount of the universe does matter take up. So you can almost picture this as like a pie graph or something like that. And if the whole pie represents the total critical amount, how much of this does matter take? How much of that does radiation take? And how much of that does dark energy take? So they're all ratios. They're all constant amounts, right? And what we'll do is we'll give them a new name. We'll call rho m. We'll call rho m to be rho m over rho crit. Sorry, to be the 1 second here. No, I do not want to add that. I want to add this. So we'll define rho m over rho crit to be omega m. So this is just a number, dimensionless number. Rho rad over rho crit to be omega rad. And then same thing for dark energy. So these are all definitions. This is nothing new. These are all constants. And if I take these definitions and put them back into my FRW equation, I'll have omega m, omega rad, omega lambda minus k c squared over a squared h squared. Okay, so one last step over here. What we're going to do is take all of these and add them up together. Call that omega total. So that I have 1 minus omega total is equal to minus k c squared over a squared h squared. And this is really it. I said I wanted to rewrite the FRW equation in a way that's a little more convenient to determine the curvature of the universe, and this does exactly that. So you can think of it this way, and I mean this is the way to think about the FRW equation. You can go out and you can measure exactly how much radiation we have, exactly how much dark energy and how much matter we have, and then all you need to do is find out what rho crit is. And we actually have calculated rho crit. Since this is 3h squared over 8 pi g, like that, 3 over 8 pi g, this is just a constant. So the only thing we need to go get rho crit is h. And as we've said today, that is also a constant. Today, h squared is basically just h naught squared because of dark energy. And so as a result, all we need to do is measure this h naught term, which we don't quite have yet, but we're close. And so we find that rho crit is approximately equal to 8.72 times 10 to the power minus 27 kilograms per meter cubed, approximately today. So with this rho crit, what we can do is we can calculate what this is, what that is, and what these terms are. We can find omega total. And then with omega total, all we need to do is take 1 minus that term, and we can compute at least the sign of k. And so overall, what's going to happen here is that if omega 0 or omega total is greater than 1, then the left-hand side is going to become negative. So my curvature will be larger than 0. Right? If omega total is exactly equal to 0, then what will happen is that, if my omega total is exactly equal to 1, then my left-hand side will become 0, and this will tell me that k is equal to 0. And then finally, if omega total is less than 1, then 1 minus something is going to end up being positive, and that means k will be saddle-shaped. And so these are 3 possibilities depending on what this total omega is. And we've gone out and we've measured this. So we've gone out and we've calculated that omega m for matter is 0.25. And that says of the critical amount of energy in the universe that would change the shape, matter makes up 25% of it. And unsurprisingly, radiation is like 0. There are not enough photons to really make anything up. And the last one, dark energy, is a whopping 75% of the overall energy budget of the universe today. So if you took a pie graph and you go look at that pie graph that I showed you earlier, matter would be something like this. There's no point even drawing the radiation amount. And then finally, the overall dark energy stuff would be the rest of it. So this would be dark energy stuff. And then if you add them up together, obviously, you get something which is very, very close to 1. And if you add something which is very, very close to 1, then we are effectively in this region over here where k is very, very close to flat.